That would be nice. Okay, fine. Thanks. No. I just have a few notes I want to put there. So I want to talk about two aspects of collider physics today. First, a little bit briefly, I want to talk about some of the physics motivations and opportunities for 100 TeV colliders. Secondly, I want to talk about, I'm talking about that a little more briefly because I think a lot of the basic physics is more familiar to you guys. But I also want to talk about a totally different opportunity for collider physics in the sky from the CMB and large scale structure. And actually, in setting up for the second discussion, I'm also going to review some very basic things about particle physics, collider physics, for ordinary particle physics. It'll both be useful for our discussion of UV completion tomorrow, and it'll be it's also good general knowledge to have about why we can be so confident in the way we go about looking for resonances. Some of my discussion this morning is going to have hopefully good complementary overlap with the wonderful things that you're about to hear from Cliff Chung when he starts lecturing. Okay, so first let's talk about the physics motivations for 100 TeV colliders. Well, for just the next generation of circular colliders after the LHC, both Higgs factories and 100 TeV colliders. So we want to have the motivations for great big colliders. What people are talking about are things that might be around 100 kilometers around. And in the first phase, you could collide electrons and positrons with a center of mass energy around 250 GeV, 240, 250 GeV. And this could operate as a Higgs factory, producing millions of Higgses. And in a second phase, in exactly the same tunnel, this is very much like what we did with LEP and the LHC. We could collide protons with a center of mass energy of about 100 TeV. Okay? And this is a set of ideas now that's being seriously discussed at CERN. It's being seriously thought about in China. And it's interesting to think about because first, there are extremely important physics issues at stake that very likely only these machines will help us settle, and that's what I wanted to spend a little bit of time talking about. And secondly, there's a lot of interesting new phenomenon and new things that happen when you go to a 100 TeV collider, especially. You're not just scaling everything up by a factor of 7 from the LHC. There's some qualitatively new physical phenomena happen that are interesting. And similarly, in order to exploit the full potential of E plus E minus collisions that could produce millions of Higgses, up to 10 to the 10, 10 to the 11 Zs, if you go back to the Z, so a factor 100,000 more Zs than we got at LEP, in order to fully exploit that also requires thinking about a whole bunch of new and interesting physics questions that we weren't thinking about before. So what are the motivations? What are the motivations for this project? Well, motivation number one, which is implicit almost in everything we do, but which we can say explicitly, is that it's the frontier. There's absolutely no reason not to keep going. We've been doing experiments like this for 100 years. Especially the leap to 100 TeV is not something crazy. It's basically the machine that we're talking about in the US in the 1990s that was canceled the year I started graduate school in 1993, the SSC. That was basically this machine. We're just talking about a factor of 2 higher in energy than the SSC. And and the number one reason for, so, we don't have to enslave, it's not like the pyramids, we don't have to enslave half the world's population in order to build these things. It's more or less something we were talking about making already 40 years ago. And the absolute dominant reason to do it is just to explore, to go and see what is there. That's reason number one. But there are a number of very important physical questions that we're certain to get an answer to by going to these next machines. And you might say that, look, before the LHC, we knew that something had to be there because something had to unitarize WW scattering. We knew that something had to be there in the accessible to the LHC. But here we don't. Okay, so here, if we don't see any new particles at the LHC, and for the purposes of this discussion about these machines, I'm actually going to assume that. Okay, so of course, if we see new particles at the LHC, it's much more obvious that that you're going to keep going for a variety of reasons. But just for the purpose of discussion, I want to assume that it's the 2020 and there's a Higgs and nothing else at the LHC. And there's some fraction of people in the field who will say, it's time to take our ball and go home and do something else with our life, and it's all over. And this is very much related to the attitude that I was mentioning in the beginning of the talk yesterday. Okay, which is, if your definition of new physics is new particles, then if we see the Higgs and nothing else at the LHC, there's no known specific energy scale where we're guaranteed to see new particles beyond that, right? Up until the Planck scale, or maybe the right-handed neutrino scale, or whatever, but some incredibly high energy scale. And so, if your definition of new physics is new particles, then we're not guaranteed to see them. Okay, and if that's the case, and you find that, and again, your purpose in life is to see plots that look like that, then and to get excited by that, then we can't be guaranteed to see things like that. Okay. However, that's not merely what particle physics is about. Particle physics is study of the fundamental laws of nature as governed by relativity and quantum mechanics. And that union between relativity and quantum mechanics, space-time and quantum mechanics, is still mysterious in many ways. We understand some parts of it well enough to calculate the G-2 of the electron to 12 decimal places. But there are many other aspects that we're incredibly confused about. And the heart of the fine-tuning problems that I mentioned yesterday are just a collision between our picture of space-time quantum mechanics and the vacuum. There's something in this triumvirate of things that we don't understand. Okay, So, and as I said yesterday, it's these more structural, deeper questions that have come to the fore now that we understand all the mechanical properties of how elementary particles work better. So those are the questions that are at stake. They're more profound questions. They're deeper questions. They're more structural questions. I should say, and I think this is a real test of what aspects, or it's a real way of distinguishing different psychologies and philosophies people have about what particle physics is. There are some people who would have been tremendously excited if we discovered something like Technicolor at the LHC, because, wow, 5 million resonances, and then, it's like the 1960s all over again, and we go and we figure it all out, and that would have been their greatest dream. Had that happened, I would have quit particle physics the next day. Okay. Personally, okay, just personally. Why? Because it would mean it's just like condensed matter physics. Okay, it's just like all these other things we've seen elsewhere. If we want to study exciting dynamics of quantum field theories, we can do it elsewhere. Okay, we can do it elsewhere, cheaper, more easily, and have much more fun doing it. Okay, if it's just generic quantum field theories and peeling one layer of the onion after another. But there was something really exciting, and this is at least really exciting to me. It's what got me into the field in the late 80s, early 90s, when Precision Lecture Week strongly hinted, that was not the picture of the world, okay? And that it looked like there was going to be an elementary Higgs. The elementary Higgs, despite it being the simplest theoretical possibility, is very strange, it's very shocking, it's very weird. That's not like something we've seen garden variety all over the place in the rest of physics, as I was emphasizing yesterday. So if your definition of new physics is new phenomenon, and the hope to discover new principles associated with the new phenomenon, then we actually have it already, and it's called the Higgs. Okay? The Higgs is absolutely new physics. We've never seen anything like it before. And the number one direct motivation for probing, for going to the next machines, is to probe everything there is about the Higgs. Okay, so we want to understand, is the Higgs elementary? That's the most important question. Yes?
So what if next year we
Well, if we discover supersymmetry, I would take the punishment of the 1,000 resonances. Okay. I'm about to write a paper with supersymmetry and 1,000 resonances. So consistency is a hobgoblin of mediocre minds, but even so. Okay. You're a mean guy, though. So in the other context, I promised to kill myself if the Higgs was spin 2. I'm curious what you would have said then. All right. Now I feel sad. All right. So this is the burning question. And what do we mean by elementary? Well, you all know there's no invariant notion of elementary particle. What we really mean is whether it looks point-like on scales comparable to its natural Compton wavelength. Okay? So long before people went to see that the proton had a size, we knew that the proton had to be composite because its G factors differed very significantly from 2. Okay? And so that's because it had been looked at by bouncing photons off of it. Okay? That's the coupling of 2 protons and a photon, which is being measured by the G factor. All right? So now, the picture that we're going to get from the LHC, even if we run the LHC till we're blue in the face, is that the Higgs looks somewhat elementary, right? So this is the burning question, if it's elementary. If it's elementary, elementary spin-zero particle, point-like spin-zero particle is what we've never seen before, right? So we want to check, is it really, right? We want to put it on a microscope. And what are we going to learn from the LHC? Well, we're going to learn that, if this is 1 over 125 JeV, roughly the Compton wavelength of the Higgs, then its size could be like 1 over 800 GeV. And what do I mean by its size there? As for example, we can see by how it couples to gamma gamma, ZZ, and so on. Okay. So we're going to nail some of those couplings to the sort of 10% level. That's the square of the ratio of these scales. And the corrections are the square of the ratio of these scales. And so that's the picture that we'll have from the LHC. Now, that's already heading in the disturbing direction. Okay? It's looking more point-like than other things. However, and what we're going to know from the LHC is essentially that it's as point-like as the pion. Okay? In fact, these ratios are really more or less the same as the pion, 130 MeV for the pion, and this scale is roughly the rho meson mass, 1 over 770. Okay? So what we'll learn from the LHC is that the Higgs looks point-like, but it looks about as point-like as the pion did, right? And that's not good enough, because we really want to know, is it a pion, for example? That would be one thing. That would teach us something. That was the content of Chaba's lectures, or various versions of the Higgs as a pseudo-Goldstone boson. But that's not full drama yet, right? That's not all of the seven horsemen of the apocalypse coming down with the naturalness issues and tuning and all the rest of it. It's sort of borderline, right? We want to know, is the Higgs like a pion, okay? Or not? Is it more point-like than the pion? And after the LHC, we will not know the answer to that question, even if we finish running until we're blue in the face. So there are two things that we can do by going to these machines. Let's first talk about what we can do at a Higgs factory. At a Higgs factory, when you predict, of course, the LHC is really a Higgs factory, and we've produced tens of millions of Higgses already. But as you know very well, we can only use 1/1000th of all those Higgses because the rest of them decay uselessly to BB bar and other things that are too hard to see. So the point of going to an E+E- machine is that you can make millions of Higgses. Now, it's a very nice fact. It's a gift for this project from nature that the Higgs is at 125 GeV. Because if you look at the cross-section for Higgs-Strelong, E+E- to Z Higgs, that cross-section has a peak at around 240 GeV. Had the Higgs been heavier, 180, then the peak would have been at a higher energy, and too high an energy to make it possible to go there in a circular machine without having really terrible synchrotron radiation. Okay, so if you want to go to 350 or something, then the issues with synchrotron radiation start becoming much more problematic. They're already not trivial here, but they're fine, and the cross section peaks at a place where the synchrotron radiation is still not a problem. So you can make millions of Higgses. And by making millions of Higgses, you can measure we're putting the Higgs under a microscope, and we can measure its couplings to much bigger accuracy than we can at the LHC. Factors of 10, 20, 30 times the accuracy that we can at the LHC. So what we want to do is get to this picture by looking at how the Higgs couples to Z's, okay, gamma, glue, other stuff. We want to go from this very fuzzy picture that we're going to get from the LHC to this much sharper picture that we can get from an E+E- collider. And it's actually amusing to think about all the higher dimension operators, all the dimension 6 operators involving the Higgs, and how we'll probe them. If we imagine all the dimension 6 operators, they really come in basically two types. There are ones where you just take all the dimension 4 operators in the standard model and you just add an h dagger h to them somewhere. Okay, so there are operators that are completely symmetrical under every possible symmetry, and the Higgs appears in the combination h dagger h. Okay, so for instance, you can have d h dagger h squared. That is a dimension 6 operator. Okay, so over some cutoff squared, you could have h dagger h times the various q h u conjugate, and so on. All these, what would have been the Yukawa couplings. You can have h dagger h times f squared, or glue squared, or w squared. Okay. Okay. So these are a whole bunch of. Let me not put the cutoff there. Okay. So this is one class of dimension 6 operators. There's the other class is just the Higgs dagger Higgs times the quartic, so just a sextic term. And then we have the operators that violate some of the approximate symmetries of the standard model, in particular the custodial SU2 symmetries. Okay? So here are these include the famous S and T operators. Okay? So you have operators like h dagger d mu h squared with the appropriate contraction of indices, so it's not just a function of h dagger h. If you remember, when things are a function of h dagger h, they're accidentally invariant under an SO4 symmetry, right? Because h dagger h is h1 squared plus h2 squared plus h3 squared plus h4 squared, so it's a function of a big SO4 symmetry. But with the appropriate contraction, these are not. Also, the S parameter, h dagger w mu nu h b mu nu. Okay, so these violate the custodial SO2 symmetry. All right, and by far the best machine to, by the way, of all these operators, this one is especially significant, okay? Because it just involves the Higgs. These two are especially significant. They only involve the Higgs, nothing else. Are invariant under all the possible symmetries. These things depend a little bit more on how you assume the Higgs couples to other things. Okay, this is just about the Higgs itself. Anyway, these couplings are really best probed at a Higgs factory. The corresponding scale goes up to multi-TeV, but just roughly speaking, you're getting a % level accuracy on almost all of these couplings, all these deviations. This one is particularly nice because it gives just a universal shift in the coupling of the Higgs to everybody. Okay? If you expand around the Higgs web, it's just changing the Higgs kinetic term, so it gives a universal coupling shift in the coupling of the Higgs to everybody. And that one we're going to be very sensitive to at the Higgs factory, almost to the 0.1% level. Okay? So that's something that we'll do better than the LHC almost by a factor of 30. And it's nice that in many ways the most significant, most invariant of all these operators is the one that we are going to probe the best. Okay. So if we see a deviation, great, and we're right around the neighborhood of seeing whether it's a pion or not. If we don't see a deviation, we know it's not a pion by a factor of 10. Okay. And so we know for a fact, we've learned something, right? You know, that you put it on a microscope and you learn. Does it look like something you've seen before? Does it not look like something you've seen before? And by a factor of 10, you learn it doesn't look like anything you've seen before. It's not like a pion. Okay? Now, okay, so that's whether the Higgs looks point-like to other things. But there's also the fascinating question of whether the Higgs looks point-like to itself. And that has to do with the existence of back coupling, okay? Just the self-interaction of the Higgs, period. Now, it's an interesting fact, which I'm sure you will see in Cliff's lectures. He may not emphasize it, but I'll mention it. Maybe he will. No elementary particle in the world other than the Higgs is allowed to have, or we've seen, has a self-interaction. Okay. This is by far the most basic interaction you can have in a quantum field theory, and yet we've never seen it before. Now you say, what are you talking about? Gluons self-interact. No, they don't. They change always. They change a quantum number. They change color, right? You have red, green, blue interact with each other. Never one species. 3 photons can't self-interact. Okay? There's no self-interaction for 3 photons. What about W's? The same thing. They change a quantum number. What about the graviton? Okay, the graviton has a nonlinear self-interaction. Changes helicity. Okay, it's 2 pluses and a minus. Okay. Now, it's in principle possible for the graviton to have a self-interaction with all plus, but we've never seen it. Okay, that corresponds to a higher dimension operator suppressed by the Planck scale. We're never, it's going to be ages before we see that, if it's there or not. There's no analog of that for anything else. There's no analog of that for photons, for example. There is no all plus amplitude involving photons. Okay, so we've never seen it. Nowhere. It has nothing to do with charge conjugation. Nothing. It's just impossible by Lorentz invariance, and you will see it in Cliff's lectures. And if he doesn't do it, I'll assign it to you as a homework problem. After you see Cliff's lecture, to prove that it's impossible to have self-interactions for anything other than the Higgs. It's fascinating. The absolute simplest possible interaction, we've never seen it before. Okay? So we'd like to see, is this interaction there? If we see that it's there in exactly the way we expect, first we're probing for the presence of this higher dimension operator. Okay? But more qualitatively, we're seeing whether the Higgs looks point-like to itself. Not just point-like to external probes, but whether it looks point-like to itself. Now, at the LHC, we're not even going to know whether this thing is there. Never mind to measure it. Okay? People talk about measuring it at the 50% level. But that means that it's going to be, shrug of the shoulder whether it's there or not. So what you'd like to do is to know whether it's there. Okay? And to try to measure it. Now, that's going to be difficult to do at a Higgs factory. But if you go to a 100 TeV collider, you make billions of Higgses, okay? And by making billions of Higgses, you can see double Higgs production. Double Higgs production has one diagram, which is just like our favorite gluon fusion, except with two Higgses coming out with a top loop, except two Higgses coming out and not one Higgs. But there's also a contribution from going to one Higgs and having the Higgs split in two. Okay, and so you can probe for the presence of this coupling once you make the billions of them that you can when you go to a 100 TeV collider. And people have done detailed studies. It's sort of an interesting violation of a certain kind of intuition. There were two or three studies being done by various people around the world. One study optimistically claimed 5% for the level at which you could measure it at a 100 TeV collider. The other studies talked about 12 or 13 or 15%. And so they all got together to fight and to figure out who was right. And they came back and they say they can measure it at 3% at a 100 TeV collider. Okay? So that's either very exciting or very suspicious. More seriously, it's because they figured out that if you're tailoring, you can tailor the cuts to look precisely for the signal associated with the cubic coupling that's there. And if you do that, you can do better. Okay? So that's a humongous difference. We go from not even knowing whether it's there to whether it's there. This is from the LHC to whether it's there and measuring it to the few percent level at a 100 TeV collider. Okay, so those are the two sets of. Now, of course, when you go to 100 TeV, it's the energy frontier. We go see what's there. You're sensitive to particles that are 5, 6, 7 times heavier than we can make at the LHC. Particles that we might make at the LHC, we can make at rates that are 100, 1,000, 10,000 times bigger. So all those things are obvious. But what I wanted to mention are the two sort of the two completely rock solid pieces of an experimental program that you need both of these machines for. Okay, and they just have to do with the Higgs, not about extra dimensions or supersymmetry or other things, but just what we've seen, in our hands. We've seen a particle, the likes of which we've never seen before, and we have to study it. Okay, so this is the completely rational, responsible, conservative next steps. And we're going to get a definitive answer to two questions. Does the Higgs look point-like? Does it look more point-like than any scalar that we've seen before? Yes. Okay, we get the answer to that question. Does it look point-like to itself? Does this most basic interaction in quantum field theory exist? Yes or no? Okay, so we get just the answer to those questions. Okay, now just a few other words about and that's it. Okay, that's I think given the novelty of the Higgs and the clean questions at stake, it's also interesting that since we don't know where the next scale is for seeing new particles, we're not promising seeing new particles for these arguments. You can ask then, okay, if you need precision, why do you need a factor of 100? If you need energy, why do you need a factor of 10? Okay, and not a factor of 10 million on the precision or a factor of 100 on the energy. Okay, and so you have to present a question that you're going to get the answer to with this leap, and not much more. And okay, these are the questions that we're going to get the answer to. We're not, of course, if we go even higher, we could measure this to even better accuracy. But there's a qualitative thing that we're trying to settle. Is it there? Or is it not there? And for that, we just need the next step. Similarly here, we want to see, does it look more point-like than the pion or not by a solid factor of 10? And for that, we need this leap in that position. Okay? Yes?
You're also expecting some correlation between these two, right?
Oh, yeah. Of course, we could have correlations between them. If you have a deviation in the triple Higgs coupling, then at loop level, it feeds in to deviation of the Z-Higgs coupling. But this is still the most sensitive way directly of looking for it. Okay? You are sensitive from the one loop correction to the Z-Higgs couplings to a deviation of the triple Higgs coupling at the 30% level. Okay, but we're talking about measuring it to the 3% level by going to 100 TeV. Now, let me just briefly mention some of the other physics questions that we're going to get some robust answers to. Apart from this, of course, they're all they're related. First, there's there are three broad issues. One of them has to do with the nature of the electroweak phase transition. All the issues about naturalness and WIMP, and W is for weak WIMPs. Okay, let's talk about these just quickly in turn. First, we asked for a long time what breaks electroweak symmetry, and now we know it's the there's an expectation value of an elementary Higgs. But in fact, we have no idea what the Higgs potential looks like. All we've seen are the quadratic fluctuations around the bottom. And we don't know what the shape of the potential looks like. So does it look like this? Does it look like this? Okay. We have no idea what the shape of the potential looks like, since we're only looking at little quadratic fluctuations around the bottom. Okay. Now, you might say, well, only a loon would think it looks more complicated, right? Why not just say that the potential is m squared h dagger h plus lambda h dagger h squared plus ... That's obviously right. Anything else, you're just, it's a make work project. You're trying to pretend there's something exciting when there's nothing exciting, right? Well, I think it's important to point out that the assumption that this is what the potential looks like is not a completely innocuous one. Why do we assume the potential looks like that? We assume it looks like that by making an analogy with condensed matter, right? Making the Landau-Ginzburg analogy. So Landau-Ginzburg tells you, write everything you can down consistent with dimensional analysis, and that's it. It's just Taylor. It's just a Taylor expansion. That's exactly the logic that leads to the hierarchy problem. Okay, this is not some completely innocent thing. If we do that, then we would expect that the m is near the cutoff. Okay, so if we're seeing that there's a Higgs, nothing else, it's 2020, right? Then this is not what Landau and Ginzburg expected, of course, unless there's someone out there twiddling the dials, right? In other words, assuming that that's a potential, it goes hand in hand with the series of arguments that lead us to believe in the existence of something like the hierarchy problem. In a sense, we don't even know whether we have a hierarchy problem until we've experimentally confirmed that that's the picture of the potential. Okay? It could be all kinds of other things. Why couldn't it be Higgs to the fourth versus Higgs to the sixth? Okay, that's something it could be. Maybe slightly more interesting, could it be like Higgs to the fourth log Higgs squared, a la Coleman-Weinberg? Okay. So it doesn't have to be polynomial. Maybe it's not even analytic. Okay. Now, of course, I believe this is the right answer. As a theorist, I believe this is the right answer. I believe that if we see that the Higgs looks point-like, this is most likely the right answer, and then we have to grapple with the tuning issues and what it means if we don't see new physics going along with it. Okay? But that's just a belief. If you're an experimentalist, you want to measure and confirm and actually see. And what I want to say is this is not an innocuous thing. This is important. Doing this measurement is part and parcel of experimentally establishing the foundations of this problem that we're going to have to, may or may not have to grapple with. If it looks like this, oh my God, complete triviality. Then there's a cutoff, there's a low cutoff, then we wonder why we didn't see all the other crap that went along with it. But anyway, right? So this is quite a bit interesting too, because it means that there are some other particles lying around. There's some there's a description of the physics that's not well separated in scales. Okay. So Now, what's the number one way in which these theories differ? What do you think? They all make different predictions for the triple Higgs coupling. Okay? Just because they look identical, the LHC is not going to be able to tell these things apart. Okay? For example, in this theory, the triple Higgs coupling is 5/3 what it is in the standard model. Okay? Just work it out. We're not going to know what the LHC, if that's right or wrong. Okay, so that's a big question to try to just determine what the shape of the Higgs potential is. Now, this question, trying to determine what the shape is, you can think of as trying to figure out how electroweak symmetry is restored as we go to high energy. Right? We can also wonder how electroweak symmetry is restored as we go to high temperature. And here, of course, we can't recreate those conditions in the lab. But as you know, in the standard model, there's no sharp phase transition. As the Higgs mass squared changes sign, it's just a crossover. So we might want to know, can we tell experimentally, though? Is there any way we can tell whether that phase transition was indeed a smooth crossover or not? There are even motivations for those of you who work on electroweak baryogenesis. There's even motivations to imagine that there was a strong first-order phase transition, because that could give us one of the ingredients we need for electroweak baryogenesis. But independent of baryogenesis, it's just an interesting question. Can we figure out what the phase transition looked like as we went to higher temperature? And while we can't reproduce the conditions of having higher temperatures in the lab, we can do the following. We can say that if we are to change the phase transition, let's say the phase transition was made first order, there have to be new particles coupled to the Higgs. Okay, for example, you can have an extra singlet with a coupling to the Higgs with some, and then the singlet can have a big self-interaction. Okay, so this is an example of a theory which can help you, which can change the nature of the phase transition to make it much more strongly first order. But the point is that anything which is going to change the order of the phase transition has to do two things. There have to be new particles that have to be light. They have to be around hundreds of GeV. They can't be at 2 TeV because they have to be relevant around the electroweak phase transition. Okay? So you must have particles that are relatively light, and they have to couple not too weakly to the Higgs, because they have to change the order, they have to change the electroweak phase transition. So the question of whether or not there was a first order phase transition, if there was a first order phase transition, you have to have new particles that are light in the hundreds of GeV range, and they have to have biggish couplings to the Higgs. Okay? So that gives you a target. That gives you a sharp, concrete, numerical target. You take any model, any classes of models. Okay? You ask what masses and couplings of the particles need in order to give you a strong enough first order phase transition. And then you ask, what do they do? Okay? The particles are light, they're coupled to the Higgs, so they should shift the couplings of the Higgs. Okay? And you should be able to produce these particles when you go to 100 TeV collider because they're not very heavy. Okay? And now you can ask, is that actually true? Model after model after model. Okay? Now, if we do really simple things like this, and if you were to wake up a theorist in the middle of the night and say, make the electroweak phase transition first order, that's the model you would write down. Okay? This nice big honking cubic self-coupling for the scalar, no problem. Whenever you have these cubic couplings, you can arrange it so that the thermal potential has 2 degenerate minima, which is what you need in order to get a first order phase transition. And in this model, what happens when I integrate out S? When I integrate out S just from this coupling, I get, here's 2 Higgses, H dagger H. There's S, H dagger H. And so one piece here is I get something like minus A squared over, so that I get a shift to the Higgs quartic coupling, but there's a Higgs quartic coupling sitting there already. But there's another piece that just, when I just expand the momenta in this propagator, I get exactly this operator that we're talking about, d Higgs dagger Higgs squared over ms to the fourth a squared plus dot dot. Okay? And so we see more concretely here that A can't be too small, M can't be too big if this is going to change the order of the phase transition. And in this model, essentially throughout its parameter space, where it changes the first order phase transition, you get like 5, 10, 15% corrections to the Higgs Z coupling. Okay? So totally accessible. Totally accessible. In fact, there's a bound from the perturbative consistency of the picture of about 3% for what the shift in the Z Higgs coupling is. Okay? So on this really simple theory, now if you see a shift in the Z Higgs coupling, you don't know it's this, of course. But if you don't see a shift in the Z Higgs coupling, you can say that this simplest way of changing the order of the phase transition just cannot happen. Now, you can do more complicated, you can do more difficult things to change the order of the phase transition. You could imagine that there's a Z2 symmetry so that everything has to couple quadratically. The S is charged under Z2 symmetry. Here, all the couplings are inevitably bigger because you have to use radiative effects in order to change the order of the phase transition. This is a more difficult example even for getting a phase transition to begin with, and it's more hidden. It's trying as hard as you can to be hidden from changing the Z Higgs coupling and potentially making these particles at the 100 TeV collider. But even in this example, and there's been a number of very nice papers on the subject, essentially the entire parameter space is covered by a combination of the Higgs factory for looking at shifts in the Z Higgs coupling and the 100 TeV collider for direct production of S. Okay? And direct production of S here is pretty tough. You're going through an off-shell Higgs and pair producing two S's, and it's assuming that these S's have a perfect Z2 symmetry. They don't decay back to the standard model. If they decay, they're much easier to see, and so on. But even in the most difficult case, essentially the entire parameter space that could affect the order of the phase transition is covered by a combination of the Higgs factor and the 100 TeV collider. Again, and doing more explorations like this is going to be what it takes to answer the question, why this level of precision, why this level of energy. Okay? So we don't need, we might need factor of 2. We don't need a factor of 100 higher in precision, a factor of 10 higher in energy in order to settle this question of whether there's evidence for particles that could change the order of the phase transition.
Yeah, but for this case,
yes.
The coupling is usually very large. But if you want the first order vision, it's usually
Well, but here all the couplings are relevant. Oh, in this case, you mean? Yeah. With a Z2. That's what I was saying. This is why this is a case that's theoretically difficult, and it's also experimentally more difficult. But even in this case where you're working to make it hard, theoretically, most of the parameter space is covered. In the case where it's easy to do theoretically, it's also easy experimentally, because there you have bigger effects. Okay. All right. So that's all I want to say about the electroweak phase transition, both in going to higher energies as well as going to higher temperatures. Maybe I'll say a little bit, one final aspect of this, which is one of the novelties of the 100 TeV collider, is that the 100 TeV collider is the first time we get to see the standard model gauge group in its massless glory. Okay? So it's really the first time where just completely ordinary standard model processes, you finally see W's, Z's, and tops effectively act as massless particles. Okay? And there are many aspects of this. Let me mention a few of them. Let me mention one of them, which is cool. There's a probability for radiating a gluon. Okay, probability for radiating a gluon is determined by the Sudakov factor, and the Sudakov factor is roughly speaking alpha. There's some Casimir But there's some Casimir alpha log squared of PT squared over some infrared scale squared. Okay, so this is the probability for radiation. It's a fact that that number is of order 1 in QCD processes. That means that we have jets, right? We don't just radiate 1 or 2. We have you produce particles and you radiate lots of jets. Now, at 100 TeV collider, the squared there and the fact that we're going to much higher PTs means that we start seeing the phenomenon of electroweak radiation. Okay? So we start seeing that we can radiate W's and Z's. They're not quite jets yet. If you went up to 1,000 TeV, you'd need to talk about W and Z jets, the same way we talk about gluon jets. Okay? But you start seeing them look like qualitatively like gluon. Just to give you an example, if you look at the dijet rate with at 100 TeV collider with the PTs of 10, 15, 20 TeV, then roughly 20% of the events have W's and Z's in them. Okay? So that's quite a lot. There's a lot of electroweak radiation. Another aspect of electroweak radiation is that in principle, we eventually don't have invisible particles anymore. We see electrons because they radiate photons. You see neutrinos because they radiate W's. Okay? And again, just to give an example, again, you need to go to high ratios of scales. But imagine you had a 5 TeV Z prime, and it's decaying to neutrinos. Then around 10% of the time, you see the neutrinos, at least on one side, because it radiates a W. Okay? And that allows you to do things that we don't normally think about doing. There are other aspects of this that we could talk about. For example, in around 10 TeV collisions, again, to make a concrete example, if you had a second Higgs doublet at 10 TeV, the production rate for the second Higgs doublet, you would get wrong by a factor of order 1, but by a factor of a few, if you didn't treat the top as part of the proton. Okay, so there's a top PDF that's important, just like the bottom quark PDF is important at the LHC. The top quark PDF is actually important for sufficiently high PT collisions at 100 TeV collider. So there's a lot of interesting there's a lot of interesting just standard model physics questions involving seeing the W and the Z in the top as massless particles. You can also, in principle, see that the Higgs and the longitudinal components of W's and Z's are becoming united in one object as you go to high energies. We've seen the Higgs. I mean, we could go looking for WW scattering if you want, although that's now just probing for some higher dimension operator. Okay, but the more exciting thing to see is that it's just literally true that the Higgs and the longitudinal components of W's and Z's become unified, and you can see that if you look for events with sufficiently high PT to guarantee that you're throwing the W's, Z's, and the Higgses out with PTs much bigger than the weak scale. And if you do that, then you can start seeing that the rate for Higgs production and longitudinal W and Z production start becoming equal to each other. Okay.
So if you can see the neutrino, does it help?
Well, at 100 TeV collider. I mean, it's not. No, it's just it means there's less missing energy, okay? Because even neutrinos become seen. Okay. All right. Let me just say a few words about the other two before I switch to my next topic. Looks like I won't be able to finish all the next topic in this lecture, but we'll get a good start. Now, something about naturalness. Well, this was the argument. We all expected that we should be seeing new particles at the LHC. Again, it might still end up being true. We might see stops at 1.5 TeV. Let's say that's true, by the way. Let's say we do see some new particles at the LHC. Then the fact that we haven't seen them so far means that we're not going to produce them. We're not going to produce millions of them. we're maybe going to produce 1,000 of them. We might produce 1,000 2 TeV gluinos. That's great. That's enough to know that you've made some color octet particle, maybe even to know that it's a fermion. It is not enough to call it a gluino. Okay. Similarly, if you've seen a stop, it is not enough. You might know that you've produced some color particles with the appropriate quantum numbers. You might even know they're scalars. We will not know that it has the right couplings to the Higgs in order to have anything to do with the hierarchy problem. We won't know about its in any detail about its couplings. It's different than the picture that some people imagine in the 90s, where the LHC would turn on and there would be 300 GeV gluinos, and we'd make tens of millions of them, and supersymmetry would be a background, in fact, to itself. And and these were things that people seriously thought about. Things have not worked out that way. Now, in that picture of the world, what people wanted to do was just make the big discoveries at the LHC, and then do precision measurements of use polarized beams at a linear collider to measure the couplings of the sleptons to 1% accuracy. Okay, that is not the world we live in now. No matter what, even if we produce the new particles, we're not producing them with high enough rate to be able to learn anything about what they're trying to tell us. So if we do make them, if we make 1.5 TeV stops, barely 10 of them at the LHC, we'll make 100,000 of them at the 100 TeV collider. Okay? Because the rates go up because of PDFs. The rate go up by huge factors at a fixed mass. Okay? So on the one hand, on the other hand, so that's if we do see things. If we don't see things, well, okay, it's true that when naturalness has worked before, it's worked in a big way. We didn't have to make excuses. But it's true that the degree of unnaturalness will be in some uncomfortable territory. People will shrug. People will not know exactly what to make of it. It could be 10%. It could be 1%. It could be 10 to the minus 3, depending on your prejudices. And you might just want to know whether you just missed the things at the LHC or not. Broadly speaking, the mass reach at 100 TeV collider is around 5 times heavier than what you get at the LHC for fixed, for the luminosities that the people are talking about, 5 to 6 times higher in mass particles. In some cases, it can be much higher. So just to give an example, if you think that the first 2 generation in supersymmetry, you think the first 2 generations are heavy, and the 3rd generation is lighter, and the gauginos are lighter, then you can have associated production of the first 2 generation squarks and a 2 TeV gluino, and the mass reach for the first 2 generation squarks will go up to around 35 TeV. Okay, so for some things the reach is just vastly bigger than what we can imagine getting at the LHC. Okay, but broadly speaking, you're sensitive to gluinos, squarks and gluinos up to 15, 20 TeV. Okay, so it's not a question of their being around the corner or not. If we've put 2 orders of magnitude between the scale where we haven't seen these particles and the scale of the W and the Z masses, I think that's telling us something more solid about the relevance of those ideas for naturalness. But maybe more, but perhaps more importantly, as I'm sure you all know, there are theories where the particles that make the Higgs natural are harder to see at the LHC. For example, top partners don't have to be colored, and they could just be missed. So now you can have endless arguments about the amount of model space tuning needed to make these theories work, but there are just existence proofs that it's possible. It's possible that this broad idea is right. It's been right for 100 years. Before completely throwing it out, we want to really see that we've explored every way that it could be realized. And just from the bottom up, nothing strictly tells you that the naturalness for the Higgs has got to be associated with colored particles. They could be uncolored. Then the LHC won't see them. So it's possible that this idea is still not already tuned to 10 to the minus 2, and then we're going to make it tuned to 10 to the minus 4 if we don't see anything. But that it's not tuned at all. at the LHC, and then we want to see whether those possibilities are realized or not. And they're both the Higgs factory for measuring the deviations of the couplings. Again, the new particles must couple to the Higgs. There's just no way they cannot give you a deviation in the Z Higgs couplings, Higgs to glue if they're colored, Higgs to gamma gamma if they're charged, and so on. And you have to be able to produce them at 100 TeV collider. And in these theories of uncolored neutral naturalness, people have done sort of detailed studies of what the mass reach is. And even in those theories, all the natural parameter space is covered by, again, a combination of the Higgs factory and the 100 TeV collider. Okay? So that's really a model-independent probe of naturalness. And finally, we all like this picture of WIMP dark matter. In fact, the very simplest pictures for WIMP dark matter, where it's a thermal relic, and if it's annihilating through the weak interactions, so if the W in WIMPs is really for weak interactions, then we know that the mass for these weakly interacting particles, consistent with being a thermal relic, is not the hundreds of GeV scale, but it's the multi-TeV scale. So if you have an electroweak doublet, and you want the electroweak doublet to give you the right relic, then its mass has got to be 1 TeV. If it's an electroweak triplet, it's got to be around 3 TeV. Okay, that's not our desire to hide them. That's just life. That's just what the numbers. That's just what the numbers come out to be. So it's an interesting fact that the earlier pictures of lighter dark matter, especially in supersymmetric theories, were based on an idea of a mixture between Winos and Higginos that annihilate too much and so have to be very heavy, and Binos that annihilate too little and have to be very light. Okay, so it is interesting that if the theory was completely natural from the particle physics point of view, then you'd expect all the particles are in the neighborhood of the weak scale, and so electroweak symmetry breaking should make a big difference to their mass spectrum. Okay, and so you'd expect to have a big mixing between Winos, Binos, and Higginos. So naturalness is what led you to think that it shouldn't be purely one or purely the other, but should be some reasonable mixture of all of them, and was compatible with having hundreds of GeV for dark matter. But as the theory gets less natural from the particle physics point of view, it's also less natural from the dark matter point of view, right? Because it's harder to make it a reasonable admixture of everyone. And if it's more pure and it's charged, then it has to be heavy. It's got to be 1 TeV, 3 TeV, and so on. Now the LHC is great at making 3 TeV colored particles, barely. Okay, but will certainly not make 1 TeV or 3 TeV electroweak particles. Certainly not in the most model-independent channel, which is just direct production of dark matter with radiating off a jet or a photon, monojet or monophoton. So for this purpose, what you need is an electroweak factory. Okay? And an electroweak factory for TeV mass electroweak charged particles is a 100 TeV proton-proton collider. Okay? It's like the LHC is a hundreds of GeV factory for electroweak particles, and the 100 TeV collider is a multi-TeV factory for electroweak particles. So again, people have done detailed studies, and thermal relics for doublets and for triplets are essentially accessible if you go to 100 TeV, even in just the direct channel where you have just direct production of the dark matter radiating off jets, monojet surges. If you have a whole electroweak sector, so you have cascade decays, you make the heavy ones that decay to light ones, things are much more visible, and so you have sensitivity well into the multi-TeV range, 3, 4, 5, 6 TeV, depending on the details. So these are 3 examples of important classes of questions, quite apart from the basic question about measuring the point-like character of the Higgs, where this level of precision and this level of energy is what is needed to give solid, robust answers to them. I think here for naturalness, there's one can attempt to even make a kind of a no-lose theorem, but that's not really in the spirit of any of this discussion. I think what's fair to say is that for all these questions, we get a very robust answer to them by a combination of these projects. All right, so that's it for collider physics on the Earth. And now let me transition to the second topic. How long do I have? Till a quarter past. Okay. Well, so let me just say a few qualitative things about it. So let me at least now set up the discussion for the cosmological collider. And let me start with the statement that we always make when talking about inflation to journalists. Let me just first, I think obviously inflation is the best picture we have for early universe cosmology. And apart from the horizon and flatness problems and all that stuff, which are perhaps a little aesthetic, although very important, the story of the origin of density perturbations from the expansion of the universe stretching quantum fluctuations out onto enormous length scales is one of the most spectacular stories in all of science. So that's all great. It's always been most reasonable for the energy scale of inflation to be very high. Hubble during inflation could be as high as around 10 to the 14 GeV. The energy scale of inflation could be near the gut scale. Irrespective of the bicep debacle, this is reasonable. If you were going to think about what you thought the energy scales was, that's where you think that's where you think it should be. And so something that we always tell journalists is that inflation kind of is like a big accelerator in the sky, right? We're probing, it's the highest energy processes that we have some access to. And so the energy scale is the scale of Hubble is 4 orders of magnitude from the Planck scale. Now 4 orders of magnitude is a long way away still, okay? Nonetheless, it's closer than where we are now. And so what I'd like to do in this part of the lecture, and I'll just say some qualitative things today, and then we'll make the more precise statements tomorrow, is to try to make the statement more precise and say, in what precise sense can we think of inflation as an accelerator? And something that we do with accelerators is we look for new particles, right? So how can we use inflation to look for new particles? What is the signal for new particles in the cosmological collider? Now, we know that the signal for inflation itself is that we look out on the sky and we see this beautiful pattern of density perturbations. Okay? And you're going to have some lectures from Matthias, but let me just say a few basic things. So if we look at the density perturbations, I'm going to pretend that we can measure these just in space. Of course, there's the extra complication in the CMV that we're just measuring it on a two-dimensional surface, but let's just look primordially. We have some delta rho over rho in x, some delta rho over rho in y. Okay? And just very concretely, how do cosmologists measure this? What do they actually do? Okay? What you do is, again, that's in the two-dimensional map, but you take the two-dimensional map, you literally take that W map, or the Planck map, and you say you took that delta t over t here, is some number, right? delta t over t is roughly of order 10 to the minus 5. But over here, it's like minus, it's cold. It's minus 3.2 10 to the minus 5. Over here, it's plus 2.7 10 to the minus 5. Okay? So you pick 2 points, right? You multiply the delta t over here times the delta t over t there. Now, if you just take those points, you're going to get some random number, right? If you shift them over, you'll get some other number. So what you do is you take the 2 points, you multiply them, and then you average the answer you get everywhere on the sky, keeping the separation between them fixed. Okay? So that's what you actually do. Is that clear? All right. So that's what that average sign means. Okay? All right? So, now in fact, both theoretically and for practical reasons, the way they actually do it is not what I told you. Okay? Exactly what, I mean, it's equivalent to what I told you. But you can use translational invariance. So first, by translational invariance, this is some function of x minus y, some 2-point function, let's say f2 of x minus y, right? But because we have translational invariance, we can go to Fourier space, right? And oh, okay, great, thank you, very good. So then we have some f tilde in k space, which is a function of k1 and k2, but it has a delta function for momentum conservation times some function of just k. And okay, so what we know is that this function of k is around 10 to the minus 5 squared over k cubed, roughly speaking. Okay, so that's the fact that it's a scale invariant spectrum. A scale invariant spectrum means that f has units of length cubed, 1 over k cubed, and saying that a scale invariant means that there's no scale. Okay, everything that appears there as it needs by dimensional analysis. Okay, so now of course in detail there's a little bit there are little corrections here. Okay, and so we know that it's not a perfectly scale invariant spectrum, and that departure from scale invariance is in 1-to-1 correspondence with the picture of an inflationary potential that you may or may not want to write down. Now, I'm not sure whether Scott emphasized this, but there is zero content in writing down potential models for inflation. Okay? By which I mean it has zero predictive content other than simply specifying the expansion history of the universe that you want during inflation. Okay? It's just a 1-to-1, completely 1-to-1 back and forth between the inflation history that you like and a potential that gives it to you. And in fact, if you think about the inflaton as a Goldstone boson for the broken time translation symmetry during inflation, then we can just take any scale factor that I want and integrate in this clock field that keeps track of how long inflation has been going on, and then it's describable by some effective theory with some potential. Okay? I emphasize all this just to say that all the features of the 2-point function in inflation are essentially fixed entirely by symmetries, by the assumption that we had a period with an approximately scale invariant expansion, and then everything else is just fixed by asymmetries. Now, there's a little bit more that we have to do that we can that I'm going to assume for the rest of this discussion. That 1 over k cubed just follows from scale invariance and nothing else. But you could imagine whether back then I not only had scale invariance, but I had the relativistic version of scale invariance. Okay? So in flat space, the analog of scale invariance would just be time translations, but you can ask whether I have the analog of boosts as well. Okay? Now, nothing in the data directly from the power spectrum tells us that we have to have the relativistic analog of scale invariance. But the feeling that the underlying theory should be relativistic leads us to strongly suspect that we should have the relativistic analog. And the relativistic analog of approximate scale symmetry is approximate de Sitter symmetry. Okay, so that's what gives you the boosts as well, not just the overall time translations, but the boosts of those constant time surfaces back then. Now, this has a physical manifestation, which is the speed associated, is the speed of sound associated with this clock field fluctuations, is it the speed of light or not? Is it close to the speed of light or not? If you only have scale invariance but no de Sitter invariance, there's no reason for the speed to be close to the speed of sound. There's no reason for the speed of light to be close to the speed of sound. And there's lots and lots of theories where the speed of light is much smaller than the speed of sound. The speed of sound is much smaller than the speed of light. Okay, where you badly break this underlying de Sitter invariance. Now, directly the two-point function we can't tell, but there's a qualitative prediction from the theories which have a much smaller speed of sound than the speed of light. See, when you make the speed of sound small, what does it take to make speed of sound small? It means that to make a speed of sound small, it means that pressure, gradient energy is smaller. Okay? You're making the effective gradient smaller. The extreme limit where the speed goes to 0, there's no gradient energy at all, right? You hit something, it doesn't even move in this direction. So if you imagine you write down a Lagrangian, there's a phi dot squared term, and there's a grad phi squared term, then to make the speed of sound small, you have to suppress the coefficient of the grad phi squared term. Now, when you suppress the coefficient of the grad phi squared term, you get larger spatial fluctuations. Okay? Again, let's take an extreme limit where you shut off the grad phi squared term entirely. Then a quantum field theory becomes nothing other than a quantum mechanics for several different particles. Imagine putting it on a lattice and you just shut off all the gradient energies. Then you just have a different particle at every site. Okay? And each particle has huge quantum fluctuations. In fact, it's a particle in a box, so its wave function spreads out uniformly. Okay? Enormous fluctuations. This is the central difference between quantum mechanics and quantum field theory in high enough dimensions, is we have gradient energy. And gradient energy suppresses the size of spatial fluctuations. This is why, while if we had the 0 plus 1 dimensional analog of a quantum field theory, it would just be a theory of the Lagrangian phi dot squared. So phi is like the position of a particle. And you would never talk about the vev of phi. Right? Doesn't make sense because the particle is completely spread out in any box you put it in. The vev of phi is not a well-defined notion, but starting in one spatial dimension is borderline 2 and higher spatial dimensions. The spatial gradients are so strong that they kill the quantum fluctuations on long scales, and you can talk about the notion of the expectation value of phi. Okay, so as we make the speed of sound smaller, the size of the fluctuations becomes larger. And that means that to be consistent with the size, that means that any underlying interactions that there are become magnified. So a qualitative prediction of theories where the speed of sound is much smaller than the speed of light is that the non-Gaussian interactions, and we'll talk a lot about the non-Gaussianities next time, but the non-Gaussian interactions between the infotons are much larger. And most of these theories have been ruled out by not seeing the large non-Gaussianities already in previous experiments. So not just from the point of view of theoretical bias, where we think there's some underlying relativistic structure, but also experimentally, though there's probably corners left, but the sort of meat of the verdict is in, we're going to assume that there's an underlying de Sitter symmetry, approximate de Sitter symmetry, which is being realized, which is being non-linear realized on this clock field. All right. So, and maybe I'll just make these qualitative remarks before we get more technical next time. There's an analogy between cosmology and particle physics. So let me start on the more familiar side of particle physics. In particle physics, before we do anything exciting, we first have to identify the stable particles in the world. Electrons, protons. If I'm a little bit more sloppy, let me call them quarks. Okay? So before we do anything exciting, we first have to figure out who's stable. Now, how do we figure out who's stable? We figure out who's stable because the particles that are stable have a large two-point function. Okay? They have a large two-point function. It means if you put it here and you wait a long time, very far away, you measure it again, it's still there, right? So that's so they have a large two-point function. You first have to see who has macroscopic two-point functions. All right. Now you can measure them and you can see them. See if they're there. Once you know they're there, though, all their properties are completely fixed. In this case, by symmetries, because we know we have Poincare invariance. Okay. So you just have to know whether they're there or not. But if they're there, you don't learn anything else other than that they're there. Okay. All right. So all the dynamical information has to do with the things that are not completely fixed by Poincare symmetry. Okay. Now, as you'll see in Cliff's lectures, and I will pick up again next time, things like three-particle interactions are in fact completely fixed by Poincare symmetry, up to an overall strength of the coupling constant. So these things in particle physics don't have extra dynamical information. They're also fixed completely by symmetries. So the things that are not fixed by symmetries, the first things that are not fixed by symmetries are 4-point amplitudes. Okay? And so we look at those, we study those, and that's what tells you dynamical information. Okay? That's what tells you if there's a resonance. We make a plot of the plot I've been making fun of many times in these lectures. The cross-section is a function of the energy, and we see spikes. Okay, and that's how we know that that's how we know what the masses of the particles are, and also by sitting on that resonance and looking at the angular dependence of how the final state is spat out relative to the beam, we can learn something about the spin of the particles. Okay? Now, what I want to emphasize, and we'll see next time, is that those predictions have nothing to do with theoretical physicists. Well, a very little bit to do with theoretical physicists, but have nothing to do with any models. You don't need to write down a model. You have a spin 17 particle there. Okay? You don't need to write down a model. You don't need to know what the Lagrangian is. You don't have to be smart. Okay? The goal in life in theoretical physics is not to be smart. Okay? To let nature be smart as much as possible, and to just do the next natural thing, not be ingenious or clever. And in this case, that goal succeeds. You don't have to be one iota ingenious or clever, because while we can't predict what the 4-particle amplitude is easily, although after thinking about it a little bit we can, but naively we can't predict what it is. It can depend on all sorts of Mandelstam invariants, ST and U and stuff like that. We know that because the 3-particle interactions are nailed by Poincare symmetry, that if we tune ourselves to live on a resonance, then the amplitude becomes the product of a 3-particle amplitude to make this intermediate state times a 3-particle amplitude for annihilating it. And these are fixed by symmetries. Okay, so in other words, this plot, everything about this plot, the fact that you have a resonance, the fact that you need to look for a resonance, and what the angular distribution is completely fixed by symmetries. Okay?
Only in the weak coupling.
Only in the weak, well, otherwise it wouldn't look like that, right? So if you have a plot that looks like that, if what I said is true, then what I said is true. Okay, so so now now the situation in cosmology is virtually identical. Here too, we have to begin by measuring a 2-point function that's macroscopic at large scales. Okay, it's this guy. Here too, its dominant properties are fixed. So this is the info thought. Its dominant properties are fixed by symmetries. Here it's the approximate de Sitter invariance. And now here, we can also hope to learn about something about the dynamical interactions by looking at higher point functions. Just like here we have to look at the 4-point function, the 4-point amplitude. Here we can look at higher point functions. Okay? Now, one nice difference. By the way, here in particle physics, we just talked about we need a weak coupling. Okay? And of course, in the standard model, we have a weak coupling. In many of the extensions in the standard model, we're thinking about having weak coupling. Here, we definitely have a weak coupling. Unfortunately, it's really weak. The coupling is Hubble over M Planck, or Hubble over some high scale. It's a very, very small number. Okay? But nonetheless, we can probe for the existence of other particles and other interactions and resonances and all, just exactly what we do in the particle physics by looking at patterns in the three-point function. Now, here's the small difference. Here I told you that the three-point function is fixed by Poincare invariance. And it's true that if we had perfect de Sitter invariance, in fact, if inflation never ended, if we had perfect de Sitter invariance, then it's true. The three-point functions are indeed completely fixed by Poincare symmetry. However, we don't have perfect scale invariance. We have some epsilon here. Okay, we have some slow roll. So, in fact, it turns out that the three-point functions that we can measure in inflation are actually parametrically epsilon times some four-point function in the underlying approximate de Sitter space, where one of these legs is thought of as being the inflationary background. Okay? So, measuring three-point functions in the sky is actually measuring essentially the same thing that we measure in particle physics, measuring a four-point function. Okay? There's a little bit different in the kinematics because one of these things has no momentum. Okay? And so this thing is a function in momentum space of three variables, k1, k2, and k3. And so that's the wealth of information that we have in large-scale structure and the CMB. Once again, you can measure them by taking delta rho over rho at 3 points, multiplying them, averaging over all of the regions in the sky with the shape of the triangle fixed. Okay? We can do the analog in momentum space, and this is the object which contains all the same information as the analogous questions in particle physics. And next time we'll talk about what features of this three-point function encode the presence, mass, and spin of particles that could couple to the inflaton. Okay? So that we can establish the complete dictionary between cosmological collider physics and particle physics. Okay? There's a lot of things up there around 10 to the 14 GeV that might be interesting to see. And we'll talk about some of them. We'll talk about them in more detail tomorrow. All right, that's it. Thanks. We'll talk about it next week. Yeah, but it's because sure. It's really because